Hello everyone, this is the first of a set of, I'm hoping, 3 or possibly 4 lecture videos on this competency energy conservation strategies to reduce the use of fossil fuels. So this whole lecture videos are about the fossil fuels. And in the first minutes, I'm going to be talking about the nature and origin of fossil fuels. In this case, we're talking about coal, natural gas, and petroleum. Petroleum is just the name for oil. We call it oil, but the better term for oil that actually gets pumped out from the ground is actually petroleum. So how does fossil fuels, how are they formed? They are formed, the reason why they are actually called fossil fuels is because petroleum, oil, natural gas, and coal are actually byproducts of dead living creatures. Okay, petroleum and natural gas, okay, is actually created from the death of marine animals. Okay, and when we talk about marine animals, we're talking about animals that actually live in bodies of water. Okay, and we're talking about a process that actually is hundreds of millions of years in the making. So what happens is oceanic creatures die. They obviously sink to the bottom. They get degraded by bacteria. And then as years go on, this sediment then gets covered up and they get deeper into the Earth's core. And as they get deeper into the Earth's core, they get heated. And as they get heated, what happens is a process called pyrolysis actually occurs. You don't need to worry about that. But what happens then is this remnants, okay, of this living creatures many million years ago then gets trapped between rock sediments, okay, and what happens is when they get trapped between rocks, okay, there is actually high pressure in those areas, and obviously, as you go deeper into the Earth's core, it gets hotter. So these two conditions of high pressure and heat creates these concentrations of hydrocarbons. Okay, so fossil fuels are actually hydrocarbons, and the reason why most scientists also call them hydrocarbons is fossil fuels, all 3 classifications, are primarily made up of carbons and hydrogens. Sometimes there are impurities present in hydrocarbons, and those hydrogens can actually be replaced by oxygen, sulfur, and nitrogen as well. These are impurities, so you actually don't want that to use as fuel. You actually just want pure carbon and pure hydrogen in most instances. Okay, so that is actually how fossil fuels are formed. The only difference between petroleum and natural gas, okay, and they happen together, petroleum and natural gas happen together, and here if you actually can see this actually shale, oil and gas shale, you'll actually have natural gas on top, you'll actually have oil in the middle, and down below underneath it in this actually not an aquifer, but in this shale is actually going to be water. All right, the only difference between oil, natural gas, and coal and natural gas is coal is actually formed in land masses. Okay, coal is primarily from plants, the death of plants, in this case inland. All right, so that's the main difference between petroleum, natural gas, and coal. All right, so that's that. So most of the world oil reserves in this case are actually in the Middle East, shown in green here. So if you look at this in this actually image here, green is actually the Middle East. Okay, blue is actually Russia. Okay, and other Russian old Soviet republics. That is Central America, Central and South America. Okay, this is us. The orange is us, and then obviously the rest of the world is actually shown here. So a lot of the oil, as you can see, is actually from the Middle East, and the reason why that is because the Middle East used to be covered by a big ocean, and obviously in the previous slide I already talked about the fact that you actually have in this case a lot the result of like gas in this case, and actually not oil, actually comes from the death of oceanic creatures. And because the Middle East 600 million years ago was covered in this huge ocean, okay, that is the only reason why the Middle East is actually where you find a lot of oil reserves in this case. All right, oil reserves doesn't mean its potential. It's the potential is there, but just know that that is actually where the bulk of oil that we know of is there. Now the only reason why these numbers have increased is because technology has actually progressed. Okay, so as we get better in terms of in this case of exploring, oil exploration, and the technology like associated with that, we are actually figuring out more that the actual reserves actually become greater. Okay, it has always been there. It's just it probably is, as probably years go on, these numbers can actually fluctuate depending on how technology improves based on oil exploration. Okay, so petroleum, which is pumped out from, in this case, from oil wells, is actually not usable in its current form. So the way that we actually make it usable is through the use of distillation. Distillations actually occur in oil refineries. Okay, so oil refining is actually happens. So what happens is crude oil activity. This is actually a mistake. It's actually pumped out down more in the bottom. This is actually heated right in the bottom. So the heat is so intense, as you can see, the heat at the bottom is around 650 to 1000 degrees Fahrenheit. Okay, so what happens is at this high heat, all right, and this temperatures, ladies and gentlemen, again is again in Fahrenheit. So as crude oil, okay, gets pumped down at the bottom of the column, what happens is some of the components of crude oil, actually a bulk of the components of crude oil turns into gas. Okay, off they go. But some of them remain liquid or solid, in this case, semi-slurry. That's what we call it, right? So it's part solid, part liquid. And that slurry then is actually what we call heavy gas oil. All right. And I'm going to talk about fluid catalytic cracking eventually in this case. So what happens is, okay, so at this temperature, some of it remains a liquid and they get pumped out. But then what happens is most of this actually turns into gas. And what happens is some of these components, as it hits a cooler region of the distillation column, they go back from gas into liquid. And so they get pumped out, right? Then whatever remains here, now again, gas is going here. So whatever, now some liquid gets pumped out, but as they go up, they turn into, again, guess what happens? This gas, whatever remaining gas, it hits here, it becomes a liquid again, and then they get pumped out. All right, all the way up, and it turns to liquid again. That's gas turns into liquid again, and then gets pumped out. All the way at the top of the column, which is around less than 90 degrees Fahrenheit, like all of that remains a gas. They no longer turn back into liquid. I'll let you cool it down further. And actually they get pumped out as actually gas. So if you look at this actual column at a 650 to 1000, okay, if you look at this, and again, what happens is you're going to have a mixture of solid or liquid on the bottom and gas on top, and then varying components in the middle. All right. So that's, and now why is this technique so important? And the reason why this technique is important, and the reason why a lot of components of crude oil boil at different temperatures, is because butane, if I'm just going to use butane, butane has, methylprop-but has actually 4 carbons. All right. Heavy gas oil has around 80 carbons, approximate. Okay. Gasoline is around octane. Okay. So we're going to be talking about 8 carbons, and around, like kerosene and diesel fuels, you actually probably have around 12 carbons. So the difference in boiling points, and boiling is the temperature in which a liquid turns into gas, of these components of petroleum oil is dependent upon the number of carbons in each component. So the more carbon a component has, the higher their boiling point. The smaller the carbon component, okay, the lower the boiling point. Okay, and so what happens is, okay, so now obviously all of these things are, you can use this straightforward from here, but what happens is you can refine it further. All right, and I'm just gonna talk about a couple of processes. Hydrotreating, what happens is you'll actually have some carbon components. Now obviously these are not pure mixtures that actually come out. This is not just all 4 carbons, not all 8 carbons, not 12, all 12, not all 80. You'll always have a mixture of stuff, of impurities. In hydrotreating, okay, I'm actually talking about hydrotreating here. What actually you do is the reason why it's called hydrotreating is because you are inserting in this column hydrogen. That's why it's called hydrotreating. And what happens is obviously is you're trying to get hydrogen to go with carbon, and therefore you're going to get that CH. hydrocarbon. Okay. Coking, on the other hand, which is all the way at the bottom, is what you're trying to actually do is you're actually trying to get rid of hydrogen. Right? So what you're heating it so high that the hydrogen attached to carbon becomes a hydrogen gas. Okay, and then you're just left with pure carbon. Okay, and the reason why you want pure carbon is because pure carbon, coke, actually in this case has a better fuel efficiency. It actually burns cleaner, well, relatively speaking, okay, and actually burns hotter. So that's actually what you use for, in this case, furnaces, smelting. That's actually what you use to, in this case, smelt like ore, iron ore to get iron, gold ore to get gold. Okay, so that's actually what you use coke for, primarily speaking, blast furnaces. All right. So, again, there's a lot of other things here. Catalytic reforming. All you're trying to do at this process is you're trying to get products that is usable. So octane is actually a product that we actually put on our gas tank. Okay, octane rating. So 87, 89, 91, the numbers that you actually see in your gas pump for unleaded gasoline is actually talking about the efficiency ratio of octane engines. Okay, it has nothing to do about the number of octane. It's actually about the efficiency of octane. All right, so that's that. So I hope this is clear as mud. I hope that helps you understand what that is. All right. So one of the processes, okay, so of in this case of one of the current practice that we do now to actually recover gas nowadays is actually called fracking. And the reason why it's called fracking is we fracture rock. Now, why do we use fracking? So what happens is initially, if you've seen before, okay, in this case, when we tap down into proven oil and gas reserves, shale in this case, what happens is we have gas on top, oil in the middle, and obviously water on the bottom. So those are very easy to relatively easy to actually pump out, and the reason why that is because you have a rock formation in which oil and gas is actually trapped. Now, the reason why you use fracking is because the amount of natural gas, all right, is embedded, is not in between rock, it's actually between sand, all right, so or sandy creek or semi-rock formations. So what happens is, if you want to think about it, you'll have grains of sand, and in between grains of sand or grains of rock is actually gas trap. And what happens is it's very, very hard for you to get the small amounts of gas because they're trapped in between these particles of rock. So when you frack, okay, what happens then is all of this gas that used to be trapped now in small spaces get now trapped into bigger spaces. These cracks now are bigger spaces in which actually gas is actually trapped. And from there, you can then suck out this natural gas back into the actual column. Now, the problem with fracking is it uses a lot of water. It uses very, very harmful chemicals. Okay, and so this is one of the things. Now, if you have this intact, if you have this pipeline intact, and once you're done with this, what do? You seal it. Then you move on to the next one. The problem with this, obviously, is if you have, let's say we have water formations underneath, what happens? There's a potential for these harmful chemicals to actually enter the water table. And when that happens, actually the more technical term is actually the water aquifer, and whoever's drinking it from upstream or wherever, whoever taps into this aquifer, then obviously this water supply then gets contaminated. Right, so that's one of the things. The other thing is we don't really know the actual long-term effects yet of all of these chemicals, because these chemicals can actually seep up as well and can actually affect, in this case, like obviously plants, okay, crops, right? So we actually don't know the effects of there as well, right? So that's actually what fracking is. In actual coal and in most other fossil fuels, you'll actually have the major elements in coal are actually all of these things in black: hydrogen, carbon, nitrogen, oxygen, sulfur. It's actually there's actually a percentage that you actually use here. So if it's greater than 1%, it's in black. If it's less than 1% to 0.001%, it's in yellow. Everything else, it's less than 0.001%. So in coal, okay, the things that we know in coal, there's other things, there's a lot of things that's actually present And anything that has an asterisk has actually been proven to be toxic